Now let's take a look at this figure 14-2, and it deals with regular magnets. And they have an attraction and a repelling of the poles. But notice we have three permanent magnets. You have one that's permanent to the left here that has a north pole. And then just the other side of that magnet, you'd have a south pole, which is lined up to the right. Then you have a magnet that just has a permanent north and south pole. And our instructor used to demonstrate how this would be affected, see, what the effect of it would have. And he would just take and spin that rotor that this magnet represents through there, and see, you would have, when you had a north and south, you see there, that attracts, it pulls it on in. And then if you had a south pole and south pole you see there, it would repel it. The only difference here, you don't have AC alternating current that will change these poles, where this would be, in this position you see, it'd be north to north, then the alternation of the current, it would change to south. And it just keeps pulling them through there, see, because the electricity on an AC system would change these poles. So, and on each alternation, as we'll see. So that's why that the manufacturers in NEMA 1 motors and generators, they classify these motors mainly that we would use B, C, and D. And you'll find that, you know, in your table, say 430.250 and 430.251. We'll find those motors, and for example, if you had a B, Class B motor, and you bought a Class C, it'll have more torque than the B. If you bought a Class D motor, it would have more torque than the C. In other words, more starting power. It would start, accelerate the load, and drive the load on a continuous basis. But right now, this figure 14-2 is illustrating three permanent magnets and how they could be used to demonstrate a rotor and north and south pole, and that's what our figure 14-2 is illustrating to someone learning theory.